Hello, today we're going to talk about heap sorting, but in order to understand the motivation behind heap sorting, we are going to review a number of different sort procedures. So sorting is the process of ordering things in a certain order, usually by their key. And there are three things that sorting depends on: the speed of the sort algorithm, the amount of memory it requires, and the amount of programming effort that it is required to implement. So we're going to talk about selection sort, insertion sort, shell sort, and a few others. So we're going to sort things in either ascending or descending order. The listing is a binary search tree and a sorted array fetch or order log n. If the trees or the data structure is already sorted, but sorting takes time, so we need fast algorithms and good strategies. So all sorting algorithms repeatedly compare two items and swap them if they're out of order. And so the speed of a sorting algorithm is dependent on how many comparisons it makes and how many swaps it makes. So for the several sorts that we're going to look at, we're just going to briefly talk about the sort and let the code remain for you to investigate if you care. In this example, we're sorting books on a shelf, and in selection sort, we pick the first element and swap it with the shortest element in the list, or the smallest, or perhaps the largest, depending on which order we're sorting in. So then the smallest book in the whole list goes to the left. So here's a way of looking at it graphically. First, we look at 15, and we swap it with 2 because 2 is the shortest element in the list. And from then on, we don't have to look at 2 anymore because 2 is in its right place. And so we'll go through this code. Selection sort is order n squared because it requires order n squared comparisons, and it only does order n swaps, one swap per element. Insertion sort takes the third book and swaps it. It assumes a sorted list, and so in A, the first element is sorted, the first book, and actually the first and the second book are sorted, but not with respect to the rest of them. So then in the third step, in part B, we take the third element, the third book, and put it in its correct place in the list. So here's the list of steps that we need to take. Remove the next unsorted book, slide the sorted books to the right until you find the right spot, and then insert the book into its new position. Here's a list of the sorted on the left and the unsorted on the right. And again, we're not going to walk through the various types of code that can provide for us insertion sort, but you're certainly welcome to look through the slides in more detail if you would like. Now, shell sort was was developed in order to make things more efficient, and it's a little more complicated in concept, but it's faster, slightly faster. So in the first step, we have this list of 12 items, 13 items, and we decide by some mechanism that we want to separate, we want to start with elements, entries who are 6 indices apart. And that's in the top slide. And we sort them according to 7, 9, and 10. So we swap 9 with 10, and then we swap 7 with 9 and move it up. In the second row in the top block, 16 and 6 are again 6 indices apart, but they're in the opposite order, so we swap them, and so forth down the list. So at the top of this list is the resorted, partially sorted list. And now we divide the 6 by 2 and get 3. And so we have a separation of 3 apart. And we do the same thing with those. We swap 7 and 4, 9 and 7. And so now the top row is sorted with respect to that row. And the second row, the same thing in the third row. And then we continue on with a separation of 1 and then a separation of 0. And at the end, we get a completely sorted list. Now the shell sort is slightly better, order n to the 1.5, which doesn't seem like much, but it's a huge improvement over, for big sorts. So merge sort divides the array into halves, sorts the 2 halves, and then merges them into one sorted array, and usually state the merge sort recursively. So if the first array is sorted and the second array is also sorted, then you go down the list and one at a time figure out which element in the 2 arrays is the smallest, and you put that in its proper position. The trick, if you will, of a merge sort is to start with the individual elements, and the individual element is, of course, sorted. 7 is greater than anything else in the list of 7. And so you sort that by merge sort, which is just to return the values. And then you look at merging the single element lists into elements of 2 that are sorted. And then you merge that into elements of 4 and so forth. Here's a diagram of it. We start out with the 4th level in this sort of tree without doing any work at all, except to understand that 7 and 5 are the individual elements in the list that are sorted already, and we sort that list using merge sort. We get 5 and 7. Quick sort takes an arbitrary entry, possibly the middle or possibly the first or last, it doesn't really matter, and partitions the array into the those elements that are less than the pivot and those elements that are greater than the pivot. And then it does it recursively. So we pick, in this case, we pick 4, index 3. We pick the element 4, and we sort things less than 4 or greater than 4. And this is the way that the first pass results in. Quick sort is quite complicated. Radix sort also, and basically a radix sort requires there to be numbers, maybe keys, integers, and the first thing we do is go from to the right digit. In other words, if you look at the top list, it's 123. We sort all the elements that are 3, 1, 2, 3, and in this case there are 2 elements that end with 0, 210 and 220. We keep them in the same order in the next step, and we use buckets to put the elements in their rightmost digit place. And then we distribute them according to the middle digit, the second, the tens element, and then so forth. So that's radix sort. So here's a list of some of the big O notation for various sorts, and we notice that radix sort is the best in all cases, but of course you got to have integers, and so preprocessing or doing something to take the keys and turn them into integers might take longer. Remember that the different growth rates are very important as n grows large. So if n is as large as 10 to the 6th, a million, n to the n log n is 19 million. N to the 1.5 is 109 million. N squared is 1 billion. So binary tree sort, we've talked about binary search trees, and if we sort into a binary search tree, we put elements into a tree that has order n log n sort effort, or order n squared for a tree with So here's the algorithm for binary tree sort, and again we talked about this before, but this is implementing putting in the blue element in each step, and at the end we have what is a sorted tree. Binary search tree is sorted according to the LNR traversal.